Well, hello to everyone again. We'll continue with the second presentation. That was, whoops, here's something. Yeah. Well, the title for this one is Materials Processing of TBCs, EBCs. But well, anyway, I think most of them are for the thermal barrier coatings and is how they are produced. Well, this one you already know how it's organized. Again, even this slide I showed you at the beginning, but is to have in mind. Please remember your substrate, typically a superalloy, a bond coat to join your thermal barrier coating with the superalloy and the TGO that is formed, okay? And obviously the gradient in temperature, because the idea of that one is to reduce the temperature. But then obviously the question is how it's produced. I mean, well, maybe as I told you that is based on layers, and yesterday I talked with you how to produce different layers. Yeah, maybe you think that it's like that, but it's not. Also, you should think that we are talking about complex structure with a lot of cavities and so on, and also that are large specimens, okay? Then the typical thing to do it is always by thermal spray techniques, okay? That is called thermal spray coatings, okay? Basically, and I will go in detail further in the slides, but that we have is we have our powder that we will inject in a gun. We will heat it, we will introduce a gas to move it, and then that will have its that our particles, or ceramic particles, will be like not liquid, not solid, is something between, or like in a molten state that we will accelerate through this energy and the gas, and then they will impact on the substrate, and there will be cold and we will be solidified again, okay? And then through that one we'll form our coating, passing several times at this spray coating, okay? Well, processes. There are, as you can expect it, several processes how to do it, and well, I found in one book, this is, I think, a good scheme of how it's organized, okay? There are mainly two possibilities, by combustion or by electric energy, okay? Well, within the combustion, the low velocity, detonation, and high velocity, mainly I will not talk about that we are more thinking is about this electric energy, and mainly through the generation of a plasma, okay? You have these APS or LPPS or CAPS that, well, obviously all of them have different names, as you see here. Also, I think I will talk about that. High velocity oxide cells, but that is more used and typically employed is this APS, this air plasma spray, or also this one, the at low pressure spray that I will show you. Wait. Well, one of the, let's say, problems is that obviously to melt or to have in a molten state or ceramics, we need a really high temperature, okay? Then depend the temperature that we will need. Well, first step by step, yeah, we'll need a temperature to melt it, and then there are obviously different techniques. We can put directly in contact with the flames, or we can go for higher temperatures to generate a plasma, and of course you will melt your specimen, but even then it's low because we should stay in a state that is between. You don't want that your particles are totally melt, okay? Only that have some viscosity. And well, other techniques. That then is also really important is the velocity that your particles are impact, okay? If they are still solid, of course you just, press your powder, but it's never attached, okay? And if it's too much, then it will be really liquid, and it's not good enough. Then it's a compromise, and you should think about the particle velocity and also the particle temperature, and after that then you can choose your technique to do it. Okay. Also, of course, depend which material you want to do it. Obviously, ceramics require higher temperatures around that one. After that, the metallic bond coats, carbides are here, and metals, as usual, cover a really large part. Okay, and again, this is important always to know the particle velocity. Okay, it's not only the temperature, the velocity with these particles moves are totally critical. Okay, to be really attached here. Oh yeah. Well, here is formulas and well, a lot of information here in the reference. You can take it only to show you that of course it's important, the trajectory, the energy, the acceleration that you send, because also it's important the gas viscosity. I will show you now one slide, but depends obviously in a lot of parameters. What is the temperature that you increase? What is the temperature of your substrate? Because also you should heat it. I mean, it depends in a lot of parameters: surface temperature, diameter, particles, several things. Okay, it's not just introduce your powder in the gun and do it. Of course, it has a lot of research below that one, but once that you have optimized, you can do something like that. Okay, well, this one is in German, but I think it's quite easy, and also then you can learn. Pull by injection of the powder. This is the reason why the German words are always so long. They collect all the words and put in just one. But well, this is just a photograph to show you, like in the first scheme. We generate here a plasma, we inject our powder, and here is our substrate. The particles are heated here because the plasma is for at this point. We melt or molten our particles and impact here in our substrate. Okay. More example, and this one is already about the different guns that could be used. The guns are that one. Okay. Well, this one is typically used for the plasma spraying, for all this one, low pressure or the atmospheric plasma spray. That is the classical one. Here there are all the name, the low pressure, as I told you, the atmospheric, that I suppose that is marked with that one because it's the most used, I suppose. Even well, it's here, I don't know why. By different techniques, but here, as I told you, here you have mainly one electrode. And here the counter part, the negative and the positive part, in order to burn out. You introduce a plasma gas. Okay, obviously you isolate everything and also water cool, because if not you melt your temperature. Here the temperature is quite hard. And on the other hand, you introduce your powder. Okay. Well, the characteristics of the powder, well, it's quite complex. In that case, you cannot produce, well, normally it's in dry powder. It's really good if your particles have a large fluidability, and then our spheres are totally recommend. And also the grain size are totally critical. But well, I think here is not the idea, is to show you how it works. Then you inject in that direction your powder. Here is the high temperature, and you have this plasma gas and the current flowing here, that you, at the end, it's on your substrate, you have your small coating. Okay. Well, here is to show you about the temperature and also the viscosity of the gas, because everything is more complex. Like as I told you, you need really defined properties. I don't want to go in detail, but of course this gas has a special viscosity, and depend the temperature that you should calculate it, because depend on particle size, the viscosity of your glass, the distance that you put your substrate, several parameters that should be optimized. And then maybe depends of that, if you need a specific characteristics, you will need different gases to move your powder. Here is more about the energy, or well, the enthalpy, as a function of temperature. As you see, the temperature is really high. Of course, it's the ionization of the gases in which parts happen, and this is quite important. Well, typically this is the gases that are used: nitrogen, hydrogen, of course argon, and helium. And here is to have an idea, of course, of the radius as a function of the temperature using this plasma. Is typical one, the nitrogen hydrogen plasma, as a function of the distance, okay, of that you put your coating. Here, as you see, the temperatures are really high. As a function of you move in the direction, and this is only in millimeters, your particles obviously are cooler and cooler. All where you melt the particles are this distance, and this is totally critical in what is the distance that you put your gun, in contrast of the substrate. Of course, also not only the temperature, also the velocity. As I told you, this is the two parameters that are more important: the temperature that you put your particles and the velocity that they impact. Depend of that, you are in the optimized part or not, combining both of them. Well, and here one example, well, obviously mostly are in German, well, mostly all of them, but is to have idea how they impact on in the temperature over a component, in what is higher noise, this plasma temperature with different conditions. As I told you, there are many things that should be optimized, depend of your powder, equipment, and so on, but just to have an idea. But obviously, they suffer at different temperature, and this is critical because that you want is a homogeneous coating. No? And here also one modeling about the temperature, but here is the gun, okay, to have idea. Here is our gun, and here is our substrate, and here is the powder that is inject, okay. Well, we inject for here, but it impact on our substrate here. And well, as it's obviously with the molten of our particles happen here, well, the plasma is it's for, and this is correspond with the injection of the particles because of course are heated and impact here. And as you see, even no farther from the flange space is really cold, and then it's critical because you need to cool down your particles. Okay. Here is another example, but in general are based in the same principle. Here is the flame sprite with a rod or with a powder, because here is your powder. You can produce like a elongated rod or a wire. You introduce your fuel. Of course, introduce the air and from the oxygen in other direction. Then you will melt it, your powder or your rod, and impact here, okay, and your substrate. Other option is the arc sprite. Again, you introduce here with, well, in this case with compressed air, introduce your powder, these wire whites. You produce here the temperature, and then impact on the substrate and produce the coating. More example, well, this one is in the other one that I told you I will mention, the high velocity oxide fuel. This works a little bit different, but in general terms are the same. You introduce now in other direction here your powder, okay, with a carrier gas. In that case, well, it's nitrogen. It's already your powder moving here instead here. Introduce your oxygen and fuel to burn out, and well, you melt here these particles. This called here shock diamonds, how it's produced, and you have your coating. Other technique, but I never see it. I mean, but that you produce is here, like the detonation of your powder. Here you cool down everything, but well, you introduce your fuel, your oxygen, obviously a carrier gas. That gas is nitrogen, and through this explosion, like a gun, and then yeah, everything goes in that direction because there are not other possibilities. You inject your powder here and impact on your coating. Okay. And other gun, this high velocity fuel sand, that thanks for this company we have these images, but mainly it's again you introduce your powder here with a carrier gas, your components, in this case oxygen propionate or propylene or different fuels. You inject and you start to melt your particles and impact here. And here is one example of this kind of guns. Okay. Other possibilities based on that, but is totally different. And this one is mainly done, I think, for the welding of the between ceramic metals components. Is by this laser spraying. You have here a source of heat that in this case is laser spray. As you see, the thermal energy is quite high, 10,000, and you melt everything. And on the other hand, or in parallel, you introduce your powder that impact here, and obviously they melt and cover these particles. You have other possibility, that is that one, because obviously with these temperatures, your material will be really affected, or depend the properties that you want at the end, but obviously they're quite high. That is called cold gas spraying. Here, as always, we introduce the powder. In that direction was from outside, but here is inner way. We introduce it, and here the thing is that the maximal temperature is just 500. But as you see here, the idea, I mean, if you can have or high velocity or high temperature, then if in that case, if we want to reduce the temperature, we should use a really high energy. And in the other, like the temperature is high enough and it's already melted, we don't need that the particles goes with a really high energy, and then the kinetic energy it's low. Okay, well, it's low, it's 1 meter per second. That is high, but it's not like that one that is really high. And that was the solution to reduce the temperature. And well, also to have an idea for you, you can, with this method, do a coating that the complete coating is from 1-2 kilos per hour, and in that case is up to 8 kilos. That is, of course, a large amount of, in terms of volume, you cover a long way. Yeah? Well, again, even more in German, but it's based in the same principle. You have a laser, a laser beam that is impact here, and from the outside you introduce your powder, and then here in the substrate that you move, it starts to produce the melting. And for example, you can produce these pieces that are like repairing. Also, these techniques are used for repairing technologies. Okay. Well, even here you can see the button for the gas turbine components. Yeah. More techniques, but mainly based in the same principle. Also to repair technologies, but based in this plasma sprite. Introduce your powder, again you heat it up, generate your plasma, and impact in your substrate. Okay. But okay, well, many techniques, and as you see, are mainly based in the same idea. You have high temperature, introduce your powder, and go with that. But the two critical factors, as I told you, the velocity and the temperature, depend on your particles and the characteristic that you want. For example, in your coating, you should choose between the possible techniques. Okay. As you see, for example, this one are more for high temperature, this one more for lower temperatures. But then, if we use lower temperatures, we will use higher velocities. Okay, it's a combination. An advantage here, well, I don't want to read the table because you have it here and you can consult by that. But of course, you have the advantage, and well, I think it's important to mention about that. That is the typical one. This one is really good, as you see, for the bonding. But well, the costs are materials, but that is quite good. I think it's important to remark is that practically for every material, it's like it's high temperature and you can control the velocity, and is that we are exactly talking about this thermal barrier coating, and also for wear protection, but mainly for the thermal barrier coatings. Okay. And here is one facility that we have in our institute. If some of you are interested to visit us, well, now it's not the best one because it's February and it's so cold, but you can go there and visit these really nice guns. Okay, this is for the atmospheric plasma sprite. Here is that you put your specimen, and well, it will impact. I think I have a couple of pictures. Well, more or less how it works. This is the facility. It's quite big. You can control practically everything here. After that, obviously, you close this door, and well, it start to work. And this is one picture how the plasma is for and the high temperatures here. And here is that well, I told you how it works. The particles cannot be totally melted. Should be something between. Well, you see here this picture. It's relative old, but it's like it works right now. I mean, it doesn't evolve. Okay. Here is, for example, well, as I told you, we have 4 particles that are partially melted and then impact on our substrate, and then they will start to form this like lamellar structure. Okay, some of them, for example, are not totally melted, then will be incorporated in this like viscous structure that at the end obviously crystallize. Also some pores that are totally required, as I told you in the first presentation, in order to have low thermal conductivity. And then pass by pass of this gun, we incorporate particles, and as you see here. Here is, for example, one example with just one particle that go through the substrate, and then we need something like that. No? If it's totally liquid, then it will go out. If it's solid, of course, it like go down. You need to produce something like that, like if you put, I don't know, paint or something really high viscosity, with high viscosity. Okay, and here is also one nice example, but it looks better here instead here by the resolution, but also is how the particles are impact, and at the end with the cooling, they are really well attached to the substrate. Okay. And here is that finally you have, here is the cross section. Okay, you apply your powder with the gun, and then we move it, cut it, and we analyze the cross section and the microstructure. And it's that I told you at the beginning. I think they look horrible. Yeah, it's like, are you sure that this work? Yeah, they work. They should be like that. This is the idea, and this is how they start to melt, and this is the porosity that we talk. But this is totally required. It's like that. Okay. Here, well, one other example about other technique that also we have here, but well, nothing special. You inject your powder from here, and here is your gas, and then you deposit in a substrate. Here also one of our facilities that again you are totally welcome to visit us. Here the technician to have an impression of how big it is. As you see, it's really big. It's within this chamber because we can control the atmosphere. Okay, here is a really long distance of the flame. Okay, that is well. Here is the picture. Here is where the plasma is formed. As you see, well, even the specimen is like here. Okay, it's really large. And with that technique, that is quite interesting. This plasma sprite by physical vapor deposition, you can produce this columnar structure that improve the characteristics of your material through this channel. Of course, the oxygen can penetrate, and is one of the problems, but it has more versatility in terms of thermal shock with the span and contrast and so on. Okay, I think we have more pictures, but probably in the future. But as I told you, one critical factor is how you produce your powder. It should be a perfect spheres, because if they have irregular shapes, they cannot flow. Okay, and you need that obviously your powder flow, and it's not possible to do it in a suspension. Okay, then it should be dry, but they flow. Then the best method is to go for spherical particles, and well, maybe well, I don't know what is your idea, but you can think that if we go, for example, to nanopowders or something like that are really small, it flows better, but it's not. It should be in more or less in that range, in more or less big particles in the stage of the micron state. Okay. In that case, well, it's alloy because that was injected with this composition, and that we do is by inducing inductive heating to melt it, you produce here, and after with an inner cut, you spark your powder, and when it cools down, like it's the minimal energy, it generates these spheres. Okay. Well, and here is also facility to generate these powders, these really nice powders, and well, after several years working on that, the group of Professor Fassen, who give me all these slides, can produce this powder. And here is, for example, extra example, because always we are talking about yttrium stabilized zirconia, but the future could be related with that zirconate. Okay. I will show you later the properties, but first we need to produce the powder by itself, and it's by solid state reaction. Then incorporate these elements and heat it at 1300 degrees, but in that case it's through a suspension with a really high content, and you do the sprites dry here to introduce it, and when they melt like spherical particles. Obviously this one maybe looks like more nicer than that one, but it's quite easy for the metals, or well, it's relatively easy to have these sphere particles, but for ceramics are quite complex, and these particles are really nice and really well produced. Okay. After, if you want to densify them, in that case it could be happen at 1400 degrees. Right. And here different particles. Okay. How they are produced by this technique. Well, again, you should optimize several parameters, but this is, on the other hand, the good part of science. I mean, you can play a lot and focus in what you want. You can have within a sphere agglomerate of several particles. For example, this is one particle, but it's not. I mean, there are thousands or millions of particles creating this agglomerate. Also, they can be agglomerate and start the densification. Then looks like more like these small particles have a state to grow. Okay. Also, if you want to do really these spheritized particles, but at the end they will be really porous, I think so, inside, or you have other possibility, of course. The easiest one, but as you see are not spherical, are sinter your powder, crush them, and then well, you have this irregular shape that probably doesn't flow really well, but probably the purity is quite high. Yeah? And more examples. This one is just one for the ceramic. As I told you, this is quite easy. You just crush your powder and then you have it. But this one is more for metal alloys. How to do it by different techniques, water atomize, gas atomize, different techniques that, well, I don't want to go in detail, but you can modify the final properties of your material. Yeah. Here is how we produce these particles and how they control the shape, and the shape is just putting like a sieve here. We introduce our particles and then they are blocked, but some of them pass, and well, we can control the temperature and different parameters first to start to characterize, not to go with the gun already with our particles. First we need to characterize them. And well, here how is the equipment is done and from the company, and also how we can control, well, different things about the peak intensity, how width is the powder or the energy. I mean, this is relatively complex, but well, now it's really well optimized, and at the end we can produce something like that at the end over really big pieces, and pieces that are totally used. It's not a lab scale. We can coat it step by step, we move it, and you coat that. You see here is the coating, and here not, and you should pass several times with the thickness that you require for this application. Okay. Also, well, here I just want to show you, because it's not only a lab scales, it's also for companies that they use for coating this kind of cylinders. For example, as you see, well, different techniques that I showed to you, and you see for different companies to do the same, they use different techniques, always the problem of the patents and something like that, but I mean, these techniques are totally used and are critical, okay? Also, other processes to use with retention in the gun support and more support from this company. I think it's a Mexican company. Well, how to inject the powder and by rotation and different things, okay? Here, well, it's just these cylinders like that one, some of the characteristics, okay, that they are coating. Here, for example, it's not just for thermal barrier coating, then they should reduce the porosity. It's the idea of the tribology. You know what is tribology? Yeah? All of you, more or less? Yeah, great. Okay, it's for wear, yeah, this kind of things. Perfect that you know about that. The oxygen, you asked me before if the oxygen is already introduced. For example, here, for this technique, it's 2%. To be honest, I have no idea about the other one, but of course, well, if you are using with gases that have oxygen or other elements, obviously you have oxygen, and always your metal particles are passivate, then you have inherent your oxygen. Probably to reduce, to use this facility like that one, that you can perfectly control all the atmosphere here, and with a vacuum pump, and it's not like the normal one. It's all this system is to extract all the let's say the atmosphere here and produce the vacuum and absorb so the particles. So yeah, probably the oxygen content is low, yeah, but it's always there, I'm sure. Yeah. And yeah, well, and different properties, yeah, about the mechanical or the hardness or the thickness depend. Again, you asked me before about the thickness in the other presentation. Well, depend the properties, you need determine thickness, and again, this is how they look like in one cylinder with the plasma spray coating. In that case, that we do is this along carbon steel. Some example to show you about well, this induction cooker is like for cooking, yeah. Yeah, they normally are require like a thermal barrier coating, okay. Well, more example about in what field can work or not in function of the technique for the thermal spray, but as you see, it's in several different possibilities. Of course, we are talking in the outside layer, and then we can modify from the mechanical, the physical, the thermal properties, of course, with the TBCs, also electrical if you want to insulate something, or on the other hand, you need to do conductive parts, chemical also for bio things, optical, I mean, practically everything. And as you see here is the total amount of this is quite high, 200 millions of euros, yeah, it's a really good thing. And well, here more examples, and well, unfortunately also it's in German, but well, I think it's no problem. Just the material, and here is why they are produced, and as you can see, there are practically all the materials can be done. Only that you need to control is the properties. And here, well, more examples about this bond coat and how they are structured. Depends what we want. You can have a really dense, less porosity, or really high porosity. Depends of the technique that you are using, and again, depend the final properties. Everything depends of that, okay? And here, well, is one technology that we use so much in our center is this suspension as plasma spray. This is like the conventional APS, is like a modification, and in that case, yeah, we introduce a suspension, because normally it's in dry powder, And then, yeah, this is exactly called here, and I told you at the beginning, normally, well, like it should be like dry powder. Your powder should have a require properties, inherent properties that not all the powders has, like this flour powder. For example, ceramics are really bad, metals are good, but ceramics are bad. And well, then you are limited by the diameter. If you want to go for nanoparticles, for example, yeah, it doesn't flow really. Doesn't flow really well. Yeah. Then also you will have at the end, obviously, different properties, and this is that they offer. Okay, obviously a new microstructure because you introduce a different particle size and different compositions. Okay, then you can have, for example, fine pores diameter or higher crack density if you need it, or high porosity levels, other phases that are produced. I mean, you are more open in that sense. And here that we do is like that. Here you have your droplet because it's a suspension. Okay, also droplets that are smaller, or even agglomerates or the particle, and you put here your heat. Some of them, like are agglomerate, okay, they are not affected by this flux. Okay, it doesn't happen because your substrate is here. Most of them are already melt, and in the correct condition they start to melt the agglomerates, and the end we have here the molten droplets, that we want to spray if our substrate is here. And there are others that pass, obviously, this liquid and this gas that are like oversprayed and cover other parts. But then at the end, that we will have is the position of our particles, even if we lose some of them. Yeah. And here is how they look like. Okay, it's like one. Well, this is like a semi-molten agglomerate of particles. Maybe you can see here. Here are really well defined these small particles here. This is the full one, and yeah, again, it's like you through something with really high viscosity here or here. That, for example, is a totally molten material. This is one of the problems with all the GaNs, that you will not have maybe all of them molten or semi-molten. It's like a mixture of them. Okay. And well, here is how it works. I don't want to focus so much, but of course, you produce here your suspension, and through pressure and different controllers, you can move your suspension, and then finally do the atomization and do the spray. Okay. Here is if we want to compare, for example, these two microstructure by the suspension spray plasma or the air spray plasma sintering. The porosity here is bigger. Well, also is obvious a crack that we want to show here, but as you see, the porosity is really fine. Instead here that is larger. There are less, but there are larger. Okay, and this is that we plot here with this SPS or APS characteristics and the pore radius. I mean, you can play with that and depend the properties for the TBCs that you want. If it's a higher temperature or it's less temperature, or with kind. Okay, I try only to show you that there are different possibilities. And here also, for example, for the thermal cycle that I told you at the beginning, this is quite important, with a temperature surface about that one. That we are working. And yeah, well, this is how many cycles they fell using a commercial powder for Toso zirconia. I don't know if you work with that, well, maybe in the Institute of Ceramic and Glass. No? Well, this is the classical supplier for zirconia. Is a Japanese company. Okay, this powder is used in tons. And well, this one is if we introduce this nano powder and do it by this spray, because then the flowability is different, and as you see, they survive many cycles. And this line, I think, is exactly the base line. If we are talking about the APS, is then the SPS, and we see if we use the nano, if we overpass this base line. On the other hand, if we continue using the same powder like the commercial in the SPS, the final properties are reduced. Yeah. well, here also a couple of examples about the cracks that are critical when you create this process, and is how they survive after the sintering. This is the sprite with this, well, 7 grams per millimeter, and here after the thermal treatment, either they survive and it's reduced or at least keep constant, okay? Well, and here a couple of pictures that I showed you about this special columnar structure. This is the top view, okay, and then we don't really see the structures, okay. We'll show you later, but looks like that. And I thought, yeah, well, are here after I will show you. This columnar, this is just the top, if we look like here, that we process with this chemical vapor deposition facility in Julis, okay, that only works in 2 millibars pressure, that is a really low pressure, and that we can do with that one is produce a really high plasma with a gas velocity in a laminar flow, and then the interaction with the surrounding atmosphere is used, and the evaporation of the powder is possible because you introduce this suspension. Okay, and here is a couple of pictures that we can do like here and here about the different nozzles or gases that we can introduce, okay? And here, well, again, a couple of examples to have an idea. Here is our gun, and here is the specimen that we want to coat. As you see, in that case, for example, we use 1.4 meters, that is a really long distance. Then the characteristics at the end will be totally different that in the typical ones that I think so. Here is one example that could work. Yeah, this one, well, I don't know the distance, but obviously it's less than 1 meter. And well, with that one, you can obtain a different microstructures. Well, and different characteristics, also how it sprays, depend velocity or the amperes that you use. I mean, yeah. And here is after that, when you introduce already your powder, and then it starts to melt here, okay, and impact finally in your specimen. As you see also, well, if your specimen is here, you lose, let's say, a lot of powder, because not all the powder that you introduce finally achieves your target, okay. But well, also you can control, depending on different processes, that one or instead that one that is more wide. Yeah? And this is the final microstructure that you obtain. As I told you, this is the cross section, okay. Here we saw the top, and like here, and this one is the cross section. And with that one, that we can create is these columnar structures that are present really good properties when for this thermal cycle process, are much better than the classical one. And well, here is a couple of examples. For example, where particles that are not vaporized and then it's like a particle, and other metal or molten powder that are not really molten by the temperature. Of course, you have a mixture of molten or non-molten particles. Yeah? And here, well, it's important thing. Obviously, is the thermal of expansion coefficient of your material against the thermal conductivity. The thermal conductivity should be as low as possible, and the thermal expansion, the idea is to have the higher as possible, because the idea is to protect the metals, and the metals has a really large one. Then we are talking that this one will be ideal, but unfortunately most of them are here. But well, anyway, there are a lot of possibilities, and as I told you, that one is quite interesting. These gadolinium zirconates, the thermal conductivity is quite low, and the thermal expansion could be better, but it's not bad enough. For example, the typical one that we are talking all the time is the yttria stabilized zirconia. Is here. The thermal expansion is better, but the thermal conductivity is higher. Well, all these values, well, all their reference here doing investigation, as well as I mentioned here, the Professor Fassen, who have who has done during several years a really nice investigation. And here, well, another example. At the beginning, on the first presentation, I showed you a problem with the heterostabilized zirconia, and then it's unfair. If I don't show you also a problem with the gadolinium zirconates, it's promising, but there are a lot of things to do. It's just a single coating, but also after several cycles, it's also these cracks, okay? And then this is totally critical, okay? Also these new TBCs often, or well, typically show low toughness, and yeah, then this is a big problem because of course the cracks can go there, and then due to the spallation of raw material, and then this is the idea of the double layer that I told you at the beginning. And okay, like with this material we can work at higher temperature, then the idea is or substrate, the famous TGO or heterostabilized zirconia, okay, but put another extra layer of this lanthanum zirconate, for example, okay, and this is that it's shown here. This is the number of cycles that unfortunately fails as a function of the temperature. Of course, if we are lower temperatures, you can produce more cycles. And when we incorporate this second layer, we are working in that range, that there are a number of really large number of cycles and at high temperature, okay. Then obviously this is more expensive, and it's more complex to process, but you increase a lot your temperature. And to have idea, here this gadolinium zirconates operates like here at this temperature, but also this possibility of the lanthanum zirconate, okay, that is working here many cycles and even at higher temperatures. But that I don't know is the lanthanum zirconate. Yeah. Then one of the small problems of these lanthanum zirconates is that the thermal expansion is low, and probably will have a problem with the metal component. But it's not a big problem in that case, because with this double layer between that one and that one is not a problem. It's only if it's in contact. Okay, well, and here I think we are close to finish. Is a couple of examples about the erosion. Okay, about the silica particles that I told you, this is totally critical because silica, the dust is critical for the turbines, and obviously we need a response as a function of the material that we use, which one is better and in which condition, and obviously depend of one is totally different. Okay, the composition of this double layer or single layers. Yeah? Well, that's all. Again, thanks to Professor Rofer Vassen for giving me these slides and this nice work. And yeah, thank you. Well, if you have questions, is the moment now or later, up to you. Yeah.
My question is about the two presentations of today. That is about the roughness of the surface that you are impacting that molecules.
In the substrate, no?
And how does it affect to the?
A lot. If you have like a poly surface,
yes,
it doesn't attach. Yeah. You need a determined roughness.
But in the other hand, you have the problem that if you have
With
so much roughness, you have the problem of the TGO. Yeah. I think it was.
Sure. Of course, but you need it. I mean, you don't have any option, because if not, they doesn't attach. They don't attach, and you need always a roughness. Also, typically, you should first do like a small grinding or the component that you want to coat. You need a determined roughness, yeah, definitely. And of course, after that, it is a problem. But even if it's flat, it's also a big problem.
Okay, thank you.
But yeah, obviously, it's one parameter. Everything that you can imagine should be controlled, and the roughness is one of them. Yeah. If you say, I mean, you have one advantage, on the other hand, you have one disadvantage. Yeah.
Okay, thank you.
Yeah. Cool. Or more questions or no? Okay, then yeah, we have finished, and the next one is, I think, is relative short. It's just a couple of examples, and well, now it's 12. I don't know, 20 minutes. 20, 30, 10. Okay, then.
Or 20.
20.